And to my beloved audience, today I will present about the experimental performance, the carbide and offset of Nanolubricant in a refrigerator system for domestic use. Okay. For introduction, I will proceed to the research background. Okay. For the research background, you know, refrigerator is the biggest space that we keep our food to make. First, we want to the main purpose of refrigerator is to maintain low temperature and extend the freshness of food by slowing down bacterial activity. However, the refrigerator system consumes high large of energy for the residential and commercial building. For measure the refrigeration system, we wish the efficiency of the system measured by coefficient of performance (COP), which is compare the cooling it produces to the energy that provide to the cooling effect. Okay. So in terms of we want to increase the coefficient of performance, some research have found that introduction of nanofluid such as Nanolubricant will improve the cooling effect and with small amount of energy. One statement that we can get from the refrigeration system is first, low heat transfer. As you know, inside the compressor already have a type of POE oil or PAG oil. This type of oil have a low thermal conductivity. When have a low thermal conductivity, the heat transfer will become slower. As such, for example, conductivity is the heat that can flow. The higher the heat transfer, the higher the flow of the heat can be used. Second, increase energy cost. By using the large amount of refrigerators, such as in commercial building, they have a large of refrigerator. The energy that they use is very large. Third, the environment impact. So on, as you know, the energy that we use is produced by our environment. The larger the energy we use, it will impact the environment, such as greenhouse gas emission and environmental damage. Okay. From this problem statement, we come up with the objective to solve this problem. Okay. For the objective, is to evaluate the effect of mass fraction of aluminum oxide and silicon carbide of Nanolubricant to the thermal conductivity. To evaluate the effect of nanoparticle volume fraction to the thermal conductivity of silicon carbide and oxide of Nanolubricant to the COP of the refrigerator system. Second, to determine the effect mass flow rate of silicon carbide and oxide Nanolubricant to the coefficient of refrigerator. Okay. Let me assume the volume fraction is defined as the ratio of volume of sustain to a total volume of mixture. The higher the volume of sustain, the higher the concentration. The higher the volume of sustain to the total volume of mixture, the higher the volume fraction. And mass flow rate is the content of the refrigeration system, is the amount of gas of refrigerant. Refrigerant that we use in the cycle in the refrigerator cycle system is the gas. Our type gas is HFS, that is hydrofluorocarbon. That is type of compressor R134A. Scope of study. In making our project, we have a scope of study. That is, first, in case silicon aluminum oxide silicon carbide and iron oxide lubricant, factors such as nanoparticle size, composition, and preparation method play a crucial role. By saying the preparation method, we have two different types. First, one-step method and two-step method. For our research, we have used two-step method. Why I use this method? Because it provides better dispersion control, breaking down conglomerate macam gumpalan, and achieve a more uniform dispersion. And second advantage is improve stability by minimizing agglomeration and setting of nanoparticle. For nanoparticle diameter, we use a small nanoparticle. We use 15 nano diameter for aluminum oxide and silicon carbide. And for volume fraction, we use 0.01%, 0.05%, and 0.1% by weight that we use in this experiment. Okay, we go to the literature review. For the literature review, actually they have two types of nanolubricant. First is mono nanolubricant, and second is hybrid nanolubricant. Mono nanolubricant is only use one nanoparticle type, while hybrid use two nanoparticle type that combine together. For the researchers, W and Salon 2028, they use a typical of nanolubricant aluminum oxide and the volume fraction of 0.1% and 0.05%. In terms of electricity coefficient, it was found that adding 0.1% of aluminum oxide to the refrigeration system result in 2.69% lower consumption compared to the base fluid. Base fluid, for example, the refrigeration system, we just use base fluid of POE in the compressor. Don't have a particle. Okay. Second, hybrid nanolubricant. We use for the researchers Sentikuma ETL 2023. Type of nanolubricant that they use is copper oxide and iron oxide, and volume fraction that they use in the unit of gram per liter. By using of gram per liter, the COP is also increased by 22% increase in COP, rising from 1.17 to 1.5 with the coefficient of 0.2. Coefficient of 0.4. Meanwhile, for 0.2, the significant increase of up to 27%. So, in summary, hybrid nanolubricant are superior to mono nanolubricant due to the synergistic effect of combining different nanoparticles. By combining them, the thermal quality increase, friction reduction where become projection, and thermal conductivity will also increase. Two-step method that I work. Okay. From the Ismail ETL 2018, he different in one-step method and two-step method. Okay. In the process of two-step method, techniques such as mechanical stirring, ultrasonic, used to mix nanomaterial with a solvent or disperse. Meanwhile, the one-step method doesn't need the ultrasonication and mechanical stirring. So, from the one-step method, is only a direct mixture of nanoparticle and base. Nanoparticle and base lubricant combined. That's all for the one-step method. Meanwhile, for the two-step method, after the combine of nanoparticle and base lubricant, he will go mixing, magnetic stirring, ultrasonication, and then it will get the hybrid nanolubricant. One-step method, the advantage is quick and straightforward, but for this method, it enhances stability and reduce agglomeration nanoparticle. This road chart is represent two statements. Okay, first, nanoparticle, aluminum oxide and silicon carbide will combine with the fluid. After that, after they combine, they will undergo process mixing atau solidification. After solidification, we use the Rosson solidifier. Okay, mass flow rate. As you know from objective, also I have stated the effect of mass flow rate. From the research, damage ADL 2021, the rise in pressure drop can be attributed to increased interaction and collision between molecules near the wall as the volume fraction of nanoparticle increase. As I mentioned about, the higher the volume fraction also give impact to the refrigerator cycle. Yes, the viscosity will be increased. So when the viscosity will increase, the mass flow rate we have to be higher. By mean the mass flow rate higher, the compressor need to working hard to give a gas to flow the higher viscosity nanoparticle to the other part. The higher instead the mass flow rate in the refrigerator system improve volume capacity and hence it transfer for more efficient and faster temperature reduction. The advantage of low mass flow rate in a refrigerator system reduce energy consumption and improve stability on stability and reliability. For our experiment, actually, in the increase of volume fraction is to higher the volume fraction is not good to FYP, because if the higher the volume fraction, this will affect the other variable such as pressure. I will explain more in my methodology. Okay, this is methodology for that. First, development of surveillance setup dan practical based certification, thermal properties, two-step method, process, stability, process and formation. Automation penggumpalan. After we proceed the stability test, we must want to insert the nanoparticle in the refrigeration system. But before we insert, we have to check automation have happened or not. If not, we can proceed to the refrigeration system. If yes, maksudnya terjadi, dia akan kembali semula ke stability test. Okay, synthesis nanofluid refrigeration. As I mentioned before, this is ultrasonification that we use. Branson solidifier ultrasonic. The use of this Branson solidifier ultrasonic is it differs than the uniform in the lubricant using ultrasonic wave. The vibration this just masuk dia punya dalam lubricant, dia akan mengalami vibration. Tapi for this out from our lab in Nadi, it also has a solidifier sound enclosure. By provide the solidifier enclosure, it reduces noise, ensure operator safety and provide a confident working environment. Because this process also noisy, so by a solidifier enclosure, this noise will be less. For electronic indicator balance is for calculate the mass of nanoparticle. The electronic indicator balance which a wind screen function is measured for precise accurate measurement of nanoparticle in nanolubricant formation. Without the screen function, the electronic indicator balance so sensitive to the air, it will affect the mass of nanoparticle that we want to measure. It minimize the influence of air movement on weight measurement, ensure relative result. After we this test tube example of equipment we use to burn our nanolubricant, and this test tube we use to thermal properties. Before we want to proceed to our two-step method, we have know the thermal property of this nanoparticle and test tube. This is the density. The higher level is for the nanolubricant and also silicon carbide. For the lower is for base tube BOE oil. The thermal conductivity of base tube and nanolubricant, we will use the densimeter. When high for specific heat and thermal conductivity, we use the KD2 Pro. Also have in the manual. After that, we get the thermal properties. We can proceed to the finding the mass nanoparticle, because we just indicate the volume fraction that we use, but we didn't indicate the mass nanoparticle that we use. So we use this formula concentration. After we use the square formula, we get the mass of each nanoparticle. For example, concentration of 0.1 amino acid and silicon carbide is volume of BOE oil. Dia akan campur dalam satu base lubricant sebanyak 100 ml, and mass of nanoparticle that we get from the formula for this. Actually, as you can see, the volume of BOE oil 100. When we use this volume of BOE oil, we use a composition ratio of 50-50. So, amino acid 50, for silicon carbide 50, to make the 200 volume of BOE oil and nanolubricant. Okay, that's it. After the two-step method, we go to study test.
Dah 15 minit ya.
Oh, dah. Saya proceed. Last. We proceed nanti. Okay. Mula saya akan continue. Kita masukkan nanolubricant dalam refrigeration system. Akan menjadi filter daya. Filter daya dia akan melapis debris of nanolubricant, andai kata ada. Lepas tu kalau itu ni ada diameter yang tinggi, diameter besar dan diameter kecil. Dia nak it want to from high pressure to low pressure flow. It will undergo evaporator. From the evaporator, the heat from the refrigerator is carried away from the refrigerator to the compressor until this condenser. Condenser is the place that it will lost ataupun haba akan dikeluarkan. Di persediaan. Sini compressor use a gas, but in condenser gas to the liquid, it will undergo the different phase, and after this evaporator, it will undergo the phase liquid to the gas. That's all from me.
Thank you. Okay, go back to your objective.
Okay.
Calculate the effect of a particular reaction of the COP. How you measure the COP?
We use the COP of the temperature of thermocouple. Thermocouple, the temperature we provide for between evaporator to compressor, one compressor to condenser, two control evaporator to the coupling tube, one, and condenser to the Capital daya 1 and contribute to evaporator 1. The total 4. That's clear.
So total 4, which one you will select? All combination or how?
Actually, we will select this as a formula. T low temperature divided by T high minus T low. So, actually, we have to undergo the experiment first to check the COP performance in the correct way or not. But we just check from the researchers. Pressure off to check the mass flow rate there.
Okay, yang second objective tu apa tak? Yang volume.
Mass flow rate.
Mass flow rate.
Mass flow.
So it should be higher mass flow rate is better lah.
No. Actually, let me see. Okay. Actually, the increase of it better, but volume fraction, the increase the volume fraction, it will make the COP decrease. At some point, it will turn. But what the effect of it jump menurun itu? It affect by the mass flow rate. Mass flow rate, as the volume fraction of fluid increase, the viscosity of non-molecule will also increase. This will increase the resistance to the flow of the refrigerant, which will reduce the mass flow rate of the refrigerant, and consequently the cooling capacity of system become lower. We reduce the mass flow rate. When we want to reduce the mass flow rate, we have to maximize the compressor to boost the mass flow rate become higher. It will also take the less energy consumption.
So dia ada optimum punya volume fraction lah. Dia tak boleh terlalu tinggi atau terlalu rendah. Okay, how you punya base fluid tu dalam bentuk cecair ataupun gas?
Base fluid kita tak dalam bentuk cecair, BOE oil.
So dia masuk dalam refrigerant tu, masuk dalam punya sistem, dia akan jadi gas kan?
Dia akan gas. Sebab dia akan melalui phase.
So dalam normal temperature, dalam room temperature dia tak meluap ke tak?
Sebab daripada
dan masa kamu nak mix the nanoparticles kan, dalam room temperature kan, dia meluap ke tak?
In the process actually my SBS DC that lepas kita siapkan refrigeration system, lepas tu nanolubricant kita siapkan, kita masukkan. Sebab actually effect the nanolubricant. So we have a liquid server to put the nanolubricant inside.
The spot tu yang masuk?
Spot tu masuk. Sebab dia effect environment.
Tu mana pakai lab mana lagi nak test? Pakai lab mana nak test untuk temperature check COP?
Apa FTP ada buku saya ambil tidak. Tempat tak dinyatakan lagi, tapi tempat nak buat tu dia di heat transfer belakangnya. Sebab kita dah provide barang benda kena ada, just set up tu kena set up.
Supervisor apa tak?
Salah.
Dia ada student lain kan?
Ada seorang lagi. Ada 2 lagi student. Satu student sama dengan saya, satu dia lain.
Okay. Dia tak masalah dulu. Result dia.
Okey.
Kau tak pakai UE apa tak kan? UE pun tak pakai. Design of experiment.
Tak
Cakap luci pun tak. Just straightforward lah. Effect lah. One factor at time. Dan parameter kamu
volume fraction and mass flow rate.
volume fraction and mass flow rate. Mass flow rate pun ni juga.
Dia macam sebab kita nak COP kita tinggi bukannya rendah. Jadi mass flow rate pun ada effect juga kat dia punya sistem tu.
Mass flow rate tu nak kamu control.
Mass flow ada pressure kau. Pressure kau.
Ada ni lah. Tepat.
Pressure kau. Pressure kau tu nak apa?
Pressure gauge tu lah.
Pressure gauge.
Kita ada mana apa? Estetik dan dia punya apa? Mass flow rate tu. Macam mana kamu nak control dia punya flow rate tu? Dia salah satu kau punya parameter kan? Macam mana kamu nak control dia punya flow rate? Mass flow rate tu? Faham? Itu salah satu kau punya parameter kan? Mesti kamu nak tahu dia punya nilai flow rate tu.
Mass flow rate ni kami
dia tak boleh control.
Kami boleh control tapi sebelum tu kami kena dapat result tu. Lepas tu kami compare mass flow tu, kami kena turunkan atau naikkan. Sebab volume concentration ni kadang-kadang saya kata 0.01%, 0.0 kadang contoh saya guna 0.1%, dia punya tu masih dapat increasekan lagi COP. Jadi andai kata nak ubah mass flow rate pun dia pun COP dah increase dah. Jadi kalau nak effectkan dia tak je, dia macam dia nak menimbangkan lagi dia punya COP tu. Kalau nak cepatkan lagi, andai kata viscosity ni tak terlalu
pekat.
nak mass flow rate ni gini lah.
Yang saya nampak lah, parameter kamu adalah volume fraction kan? Pergi pada objektif.
Volume fraction dengan mass flow rate.
Mass flow rate juga?
Mass flow rate juga sebab effect of mass flow rate pun macam saya kata lah, increase the resistance to flow of reaction will reduce the mass flow rate.
Maksudnya macam ni, benda yang kamu boleh kontrol. Parameter ni benda yang kita boleh kontrol lah. Kan? Maksudnya bila kita boleh kontrol, maksudnya mass flow rate tu kamu kena kontrol. Kan? Bukan di effect oleh volume fraction tu.
Okay, faham.
Maksudnya mass flow rate tu bukan kamu punya parameter lah. Mass flow rate ni just benda yang ter-effect disebabkan oleh volume fraction. Kan? Betul. Parameter kamu tak juga lah. Yang fraction kan. Kena compare kan? Okay, je lah. Okay, saya